Okay, move on to the final talk of the day from Andrew Lamb from Warwick, modelling surfactants and two-phase flow.
Hi, I'd like to thank the organisers for giving me a chance to speak. What I'm going to present here is joint work with Harold Garker in Regensburg and Bjornsson and Warwick. So I'm going to briefly mention why we want to model soluble surfactants in two-phase flow. I'll give a derivation of a sharp interface model, and then a phase field model, and then I'll discuss what the relationship between those two models are. So in industry, emulsification is a process where we want to mix two fluids that are normally unmixable. So in particular, it's desirable to have stable dispersions of one fluid in another. So here we have, first picture, two fluids. And when we have something like this, stable dispersions of fluid 1 into fluid 2, we call the entire mixture a stable emulsion. Otherwise, we call it an unstable emulsion. So common examples will be milk, fire extinguishers, hand cream, butter. The mixture itself is thermodynamically unstable and will progressively revert back to its unmixed states over time. So in the interest of prolonging the lives of these products, surface active agents or surfactants are normally added to increase the stability of the mixture. And so there is great interest to understand how surfactants influence the dynamics of a multi-fluid system. So a bit about what goes on. There's interfacial tension between the two fluids due to the immiscibility of the two fluids. And emulsification can only happen when the interfacial tension is sufficiently low. So what the surfactant do is they adhere to the fluid interface and creates a buffer zone. And the effect of this is to reduce the surface tension and thereby allowing small droplets to be stable within the bigger bulk of the other fluid. Surfactants here can be broadly classified into a soluble and insoluble surfactants. The soluble surfactants can exist in both the bulk fluid phases and on the interface. So for example, this picture here, the surfactant here can exist in the water phase and on the oil-water interface. We call that soluble. Surfactants that are insoluble will only exist within the interface. So if you were to introduce an insoluble surfactant into an oil-water system, they'll migrate towards the oil-water interface via a process called absorption. So the key dynamics we want to model here is the absorption process. So one of the simplest 1D model would be something like this. So I have a bulk domain omega, which is the positive real line, and my interface is the origin. C is the density of the bulk surfactants, gamma is the density of the interfacial surfactants, and this is my system here. I prescribe the far field initial concentration for the bulk surfactants, constant Cb, zero initial density for the interfacial surfactants. And in the seminal paper by Warden-Tordai, they derived an equation for calculating the interfacial surfactant as a function of Cb, and this density here, which is often called density of the sublayer. So it is the bulk phase immediately adjacent to the interface, or you can think of it as the trace of C on the interface. So I'd like to point out two timescales exist in this system. There is a rate of diffusion in the bulk and also a rate of absorption onto the interface. So if we assume that the second one is much faster than the first one, so that the interface is always in equilibrium with the sublayer, then we can prescribe a relationship between the interfacial surfactant density and the sublayer surfactant density via a function g. So in this case, this is known as the diffusion-controlled absorption or instantaneous absorption, and the g here in the literature is known as an absorption isotherm. So I've listed here 4 of the most popular isotherms used in the literature. We start off with the Henry isotherm, the linear one, and then the slightly non-linear one, the Langmuir, and then the Frumkin and the Volmers are generalizations of the Langmuir. So once you select an isotherm G, you can plug it in into the Warden-Tordai equation, and solve it using a Newton method. So here I've done it here for the Langmuir dynamics. CB here is 0.2. The red circle is the interfacial surfactant concentration, and instantaneously we see that all the surfactants in the sublayer gets deposited into the interface. And as the source here continues to supply the bulk with surfactants, the surfactants then diffuse into the sublayer, and then the surfactants in the sublayer get deposited onto the interface. So the concentration on the interface will continue to rise until the sublayer is in equilibrium with the bulk. So this instantaneous absorption assumption is useful because it helps us calculate the interfacial surfactant density using the Ward-Torda equation. But this assumption doesn't generally hold, in particular when we have the surfactants are ionic, or when the diffusion is not limited to a thin layer around the interface. But if we don't have instantaneous absorption, then we don't have a closure relation between the sublayer density and the interface density. So what we would like to do is to construct a model of soluble surfactants where we have a parameter that controls whether the absorption is instantaneous or non-instantaneous, and also incorporate absorption isotherms when we have non-instantaneous absorption. So this leads me to the sharp interface model. So the idea is, or we model the interface between the two fluids as a hypersurface, which enforces the immiscibility condition. And so any surfactants on the interface have to be modeled by surface PDEs. So to get an idea what the equation should look like, we're first going to assume there's no fluid motion, and surfactants are only soluble in one of the bulk regions. So some notation here: omega is the boundary domain RD, gamma is the interface now, and it's the boundary of some omega star, strictly contained in omega. And omega prime is the region where the surfactant is soluble, and we call density C, and C gamma denotes density on gamma. So from the basic mass balance, if we have a flux mass, bulk flux JC, test volume V, then the balance of bulk surfactant mass gives us this local law here. What we postulate is that the total surfactant mass balance in the test volume V is given like this, where J gamma is now an interfacial flux. So using transport theorem, we derive this local law here. So if we're in one dimension, the surface gradient disappears, and if we set JC to be proportional to minus the gradient of C, then these two equations gives us the one-dimensional absorption model I showed you earlier. So to figure out what JC and J gamma should look like, I introduce an energy. The energy ESI, SI for sharp interface, is composed of the bulk and the interfacial free energy with densities G and gamma. I assume that they're both strictly convex. So if we were to calculate the time derivative of the energy and using these equations, we obtain this equality here. So I'm going to make the constitutive assumption that JC is proportional to minus gradient of G prime, J gamma is proportional to minus surface gradient of gamma prime, and JC at the interface is proportional to the difference between the chemical potentials gamma prime and G prime. So we have these, plug those in, and then we obtain this energy inequality, which guarantees thermodynamic consistency. So our model becomes these three equations. So what we used here is a free energy approach, and at equilibrium, the chemical potentials gamma prime and G prime has to be equal. And so this constant alpha here can be seen as a kinetic factor, which tells us how far we are from thermodynamic equilibrium. So if alpha is positive, then gamma prime minus G prime is positive. So we are in the non-instantaneous absorption case. And if alpha was 0, then gamma prime equals G prime. And because gamma prime and G prime are monotone, I can invert gamma prime to define the absorption relation G here via this relation. So what we then do is based on the common 5 of the popular isotherms used in the literature, we worked out what gamma prime and G prime should look like. And for example, for the linear Henry isotherm, the gamma prime and G prime looks like this. And then for the more complicated Langmuir, Volmer gives us something like this. So now we add in fluid flow. One of the assumptions I have not mentioned here, I assume that the mass of the surfactants are negligible compared to the mass of the fluid, so that when we look at the balance of linear momentum, the surfactants doesn't enter into this equation. So some notation, omega I is the bulk fluid region separated by interface gamma. Ci is the density, bulk density in omega I. C gamma is the density on gamma. Then balance of fluid mass and momentum gives us these two equations. Here rho bar I is the constant fluid mass density of fluid I. And T here is a tensor, which is to be determined later. We assume gamma is purely transported with the flow, so that the u gamma is the normal velocity on gamma, matches up with the normal component of the fluid velocity. We assume there's no slip at the interface, so that the fluid velocity is continuous across gamma. And now the surfactant equation looks like this. And the only difference here is, instead of the time derivative, we have a material derivative. And this is a similar substitution for the surface equation. And to figure out what Jc, J gamma, and T should look like, we look at the energy. And the addition now here is the fluid energy, which accounts for the kinetic energy, and then calculating the time derivative of the energy and making a similar set of constitutive assumptions, we get to this sharp interface model. Equations 1 and 2, the classical incompressible Navier-Stokes equation. Here eta I is the constant viscosity of fluid I. Equation 3 is the convection diffusion equation for the bulk surfactants. Same for equation 4, we have the evolution equations for the interfacial surfactants. Equation 6 here tells us whether we're in the instantaneous absorption case or non-instantaneous absorption case. And here equation 5 tells us that the jump in the stress tensor is balanced by a sum of two forces. The first one is the curvature, mean curvature times surface tension sigma, which is defined via this thermodynamic relation. And the second one, the surface gradient of sigma, models the Marangoni effect. So our model here, this free boundary problem, extends an earlier model by both co-workers by considering a case where alpha is strictly positive. So under appropriate boundary conditions, the sharp interface model satisfies the conservation of volume of the bulk regions, conservation of total surfactant mass, and an energy equality. And we note that if we are in the case of non-instantaneous absorption, we get extra energy dissipation. Now, I've turned to the phase field modeling approach, where we relax the immiscibility assumption and assume there's some microscopic mixing of the two fluids. So we use a interfacial region of finite thickness to represent the interface, and within this region we allow the fluids to mix, and so we have to account for certain mixing energies. So we introduce a function phi, an order parameter that describes the presence of the phases, and phi maps omega 1 to -1, gamma to 0, omega 2 to 1. So in the sharp interface model, phi would jump across the interface. But in the phase field model, we allow phi to vary smoothly across the interfacial region. And the region, the transition layer here is scaled with a small parameter, epsilon, where phi varies smoothly from -1 to +1. So you can think of the phase field model as a regularization of the sharp interface model. We define an interpolation of the fluid mass density and viscosity like this. And then earlier work by Abel, Skarka, and Grun, they derived a prototype model for two-phase flow with different densities given like this. The first two equation is the incompressible Navier-Stokes equation. Here V is a volume average velocity. This equation tells us how the order parameter evolves with flux J phi. And here is the equation for the fluid mass density rho phi. And we note that if the densities are different, then we don't get back the classical equation for the density, as we will see in the sharp interface model. So our extension consists of coupling this prototype model for two-phase flow with the surfactant equations. So we used a result from ALT. Let's just go back to the case where there's no fluid and surfactant is only soluble in omega prime. So this is our system. Here J is shorthand for this difference. And the result by ALT shows that this is an equivalent distribution form for our surfactant system, where chi omega prime and delta gamma are formerly the Dirac measures on omega prime and gamma, whose definition is given like this. So if the phase field model is a regularization of the sharp interface model, we could use this and simply regularize the indicator and surface Dirac. What we do is we use the Ginzburg lambda energy density as a regularization for delta gamma, a scalar multiple of delta gamma, given here. W is a potential of double well, double obstacle type, and we denote by psi the regularization for the indicator on omega prime. One example we use in the numerical computation is something like this. And so our surfactant equations for the phase field model is simply these two equations. Note that C gamma now is a field defined on omega, and so we have full gradients here rather than surface gradients. So if we want to have non-instantaneous absorption, we set alpha to be positive, and if we want to model instantaneous absorption, we scale alpha with epsilon. So this came out from an asymptotic analysis, which I'll tell you about later. Another way, we came up with another way of modeling instantaneous absorption. So rather than scaling alpha with epsilon, we first assume there's local thermodynamic equilibrium, so that all the chemical potentials are equal. We introduce a new chemical potential Q, which is defined on omega, and we use this as an unknown variable rather than the density C and C gamma. So since we assume that the free energy densities are convex, the derivatives are monotone, and so we can define C as a function of Q like this, and C gamma as a function of Q like this. So using that, we plug those in and we add the equations together. The right hand side cancels, and we only get an equation in Q. So coupling these to the phase field model of Abel, Skarka, and Grun, the full phase field model looks like this. So the first two lines is the conservation mass and momentum. So the top, these two is the Navier-Stokes, incompressible Navier-Stokes equation. There's two extra terms to account for different mass densities of the fluid and also surface forces effects. The order parameter phi is governed by an equation of Cahn-Hilliard type. Here m phi, we choose the mobility to be a degenerate mobility or mobility that's constant but scaled with epsilon. And then our model requires the surfactant equations. And depending on what situation you're in, we have model A, two-sided instantaneous absorption, which is given here. K is a constant, so that K delta gamma converges to the delta gamma. So in the case for a double obstacle, K is usually 2 over pi. And if it's a standard double well, then it's 3/4. Model B deals with one-sided instantaneous and one-sided non-instantaneous. So the instantaneous, the side which is instantaneous is omega 2. So we can equate gamma prime with G2 prime and write C gamma as a function of C2. And then we add the equations for C2 and C gamma together into one equation for C2. And model C, the two-sided instantaneous, we use the idea of using a common chemical potential Q. So we set all the chemical potentials to be equal. Sorry, there's a typo here. And so we have one equation in Q. And similar to the sharp interface model, under appropriate boundary conditions, the phase field models satisfies conservation of volume, conservation of total surfactant mass, and an energy inequality. And we have extra dissipation if the absorption is not instantaneous. So I've mentioned that the phase field model can be seen as a regularization of the sharp interface model. And so it will be a natural question to ask what happens when we send epsilon to 0. So what we've done is we've used a formal asymptotic analysis to recover the sharp interface model from the phase field model. So more formally, if we have a smooth solution to the phase field model, such that they all have an asymptotic expansion like this, then the leading order terms satisfy the sharp interface model. I'd like to point out two new aspects of the formal asymptotic analysis regarding the recovery of this bulk flux as an interfacial source term on the surface PDE, and by scaling alpha with epsilon, we get this relationship here. So to sum up, I'm going to present some numerical simulations. In one dimension, we looked at epsilon convergence. So in the case of non-instantaneous absorption, this is the model. The first graph is the profile for C gamma through time at the point at the interface, and the black line here is a sharp interface model, and we see convergence as epsilon goes to 0. The second graph is the profile for C at the final time t equals 1 across space, and you can't see the black line, but we see convergence as epsilon goes to 0. So when we scale alpha for epsilon, we should converge to the instantaneous absorption sharp interface limit, and the same pictures here, epsilon going to 0 converges to the black line. Here, epsilon going to 0 converges to the black line. We did one more numerics on the model C, where we write everything as an equation of Q, and the black line here is the sharp interface limit with instantaneous absorption, and we see epsilon convergence for both graphs. So in 2 dimensions, we looked at the effects of isotherms on the shape of a droplet. The numerics is done by Bjornstiner. What we have here is a droplet which we expose to shear flow until it obtains a steady shape. And with our models, we could plug in what gamma prime and G prime to obtain the Langmuir, the Freundlich, and the Frumkin isotherms. So so once the droplet attains a steady shape, we introduce surfactants on one of the walls. We let the surfactant diffuse and absorb onto the interface, and we look at how much deformation there is. So here in this experiment, the Langmuir has the smallest deformation, followed by the Frumkin and the Freundlich. And then we looked at the surfactant densities on the interface, and we also see that Langmuir has the smallest surfactant density compared to the other two. But since the surfactant density is related to the surface tension, with more surfactants meaning a smaller surface tension, the Langmuir has the highest surface tension out of all 3. So I'd like to conclude that I've derived thermodynamically consistent models for soluble surfactants in two-phase flow. One is an extension of a sharp interface model, and the other is the extension of a diffuse interface model. I've given you 2 different phase field approaches to model instantaneous absorption, namely one scaling alpha with epsilon, and the other one is to use a common chemical potential Q. We've done some formally match asymptotic analysis, and we recovered a sharp interface model. The numerics in 1 dimension suggests epsilon convergence, and in 2D we looked at the effects of different isotherms. So I'd like to end with some work have to be done on the existence theory for the model equations and the convergence analysis in a more rigorous setting. And I'd like to acknowledge EPSRC and the German Science Foundation for supporting this research.
Any questions?
Have you ever heard of the overflowing cylinder experiment?
No.
Well, a standard experiment in chemistry is to have a beaker in gravity, and put some surfactant into it. So you produce a surface tension gradient across the surface, and if the beaker is right full, it starts to flow over the edge. We think you could analyse that, because there you get the rate of change of area, which is a crucial thing in the surfactant drive mechanism, which you don't see so much in your droplet, I don't think.
No, so in the 2D experiment, we're only interested in comparing the effects of different isotherms.
We want to see the flow that's generated.
Oh, no, we didn't do that. We only it's because how our model is structured. It's quite general. We only have to pick particular forms for gamma prime and G prime to achieve different isotherms, and we just simply thought about.
Do axisymmetric, but in a cylinder.
We could do that.
Any other questions or comments? Okay, well, thanks, speaker again.